welcome to my math tutorial. It's the first video that I've done, so if you're watching this from the future, when I'm a superstar millionaire, this is how it all got started. And it's probably going to be terrible. The reason I'm making this video is because for my complex analysis class, instead of a final exam, we were instructed to make an educational video about one of the topics we covered in class. So, let's see how this goes. The theorem that I want to show you guys today is one that's called Cauchy's residue theorem. It's very important in evaluating many kinds of integrals, so I want to do three things in this video. I'm going to teach you guys what a residue is, I'm going to prove the theorem to you guys, and then we're going to do a few examples. First off, let me explain to you guys what this theorem says. We start with our usual suspects of assumptions. Our domain D is simply connected, C is closed and simply connected, and our function f is analytic across the region. We also want to make sure we have some singularities within our closed region. These are places where the function is undefined, usually because we'd be dividing by zero. These have to be isolated singularities. They can't be branch cuts. We can have one or we can have a lot of isolated singularities within our region. Finally, we can say that the integral of the function over this closed region is equal to 2 pi I times the sum of all of the residues of the singularities. That is Cauchy's residue theorem. Now then, let me tell you guys what a residue is. When I first heard of residues, I didn't like the idea because residues are a messy substance. But that is not what this kind of residue is. No, this kind of residue is based on the Lorentz series of a function. If you recall what a Lorentz series is, it is an expansion of a function about a point z0, and it expands into an infinite sum of terms that have the powers of z going from negative infinity to infinity. The coefficients of the powers are a, with the subscript of a corresponding to the power of z. The residue of this function is simply this coefficient right here, a sub negative 1, the coefficient of the z to the negative 1 term. We write it out this way, saying it's the residue of a function at the point z0. Now then, how exactly do we extract this term from the function? Well, we can do it one way for a residue of a simple pole, and then another similar way for a residue of a higher order pole. I'm going to write out the Lorentz series of a function for a simple pole, which usually means it has a z to the first in the denominator. This function f0 is simply our original function without the pole, and we write it over our pole just to make it easier to see. This function is equal to a sub minus 1 over z minus z naught plus a naught plus a sub 1 times z minus z naught plus a sub 2 times z minus z naught squared, and on to infinity. And this is all our original function. Now then, this term right here, the a sub minus 1, that's what we want to find. So we're going to start by isolating it, multiplying the whole function by z minus z naught. Doing that raises every power of z in our Lorentz series up by a power of 1. That makes this a sub minus 1 term a constant, and every other term gains a power of z. So the question is, how can we extract just this one term? Well, by evaluating the function at z equals z naught, every term will cancel to 0 except this one constant term. But we can't actually let z equal z naught, because according to our original function, that would mean we would be dividing by 0. So what we can do is take the limit as z goes to z naught. That will give us our a sub minus 1 term, because this term will equal 0, this term will equal 0, and all these infinite amount of terms will go to 0. And what we are left with is our residue of our function at our pole. For a higher order pole, we start the same way, except instead of having a z to the negative 1 power, we have a z to some negative n power. The Lorentz expansion for a function like that is very similar, but it has n terms that are raised to a negative power. To extract our a sub minus 1 term, we're going to get rid of all the z's in the denominator by multiplying the function by z minus z naught to the n. That will leave our a sub minus n coefficient a constant, and all other powers of z go up by n. To get rid of the z's attached to our a sub minus 1 number, we're going to take n minus 1 derivatives of our function. That will bring every number before it down to 0, leave it a sub minus 1 a constant, and then the infinite amount of terms in front of it. It's important to notice that because of the derivatives, we now have n minus 1 factorial multiplied by our a sub minus 1. So I'm going to do two steps in one. I'm going to divide our equation by n minus 1 factorial, and then just like for a simple pole, take the limit as z goes to z naught. There's our residue. The next stop in our adventure is Lorentz theorem, which tells us how to find the a sub k coefficient for the Lorentz series. The coefficient is equal to 1 over 2 pi I times the integral of the function over z minus z naught to the k plus 1. Do you see this thing? This thing right here, this is what we were looking for at the start of the video. Can you see how we're going to find it? We're going to get this for k equals -1. This means the z minus z naught is raised to the 0 power, which is 1, and our a sub minus 1 term, our residue, is equal to 1 over 2 pi I times the integral. Or, our integral is equal to our residue times 2 pi I. If you remember, Cauchy's residue theorem states that the integral is equal to the sum of all of the residues of the function inside our boundary. What we need to know is, why is it the sum? Why don't we multiply them or something? Well, when we integrate a function over a region that includes several poles, we can break the integral into other regions just around the poles. This is because, where there isn't a pole, in this big red area, the integral across that region is just 0. This is called Cauchy-Gorsat theorem, if you're interested. So the total integral is just the sum of the integrals around the poles, and so we get a sum. Dun 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 dun! We have successfully proved Cauchy's residue theorem. Now it's time for an example. Let's start off with a simple one. Our function is f equals z plus 3 over z plus 2. Our pole here is z equals -2. The integral of a region around that pole is 2 pi I times the residue of the function at z equals -2. We multiply the function by z plus 2 and take the limit of what's left as z goes to -2. We are left with the value of 1. So the integral of this function is 2 pi I times 1, which is 2 pi I. Okay, that one was way too easy. Let's do this one. Let's let our function be 1 over z squared plus 9. This is the same as 1 over z plus 3i times z minus 3i. We're going to let our bounded region be just this pole right here, where z equals 3i. Since that is the only pole in our region, we only need to find one residue. So our integral is going to be equal to 2 pi I times the residue at z equals 3i. We multiply our function by z minus 3i and take the limit of what's left as z goes to 3i. We get 1 over 6i, or -1/6 I if you rationalize. Multiply this result by 2 pi I, and we find that our integral is pi over 3. Now then, let's do this one. We're going to let our function be z plus 2 over z to the 4th plus 2z cubed minus 2z minus 1. Our boundary is going to be one that involves all poles. This denominator factors into z plus 1 cubed times z minus 1. As you can see, this is going to be an example involving this higher order pole at z equals -1. So our integral is equal to 2 pi I times the sum of our residues at z equals 1 and z equals -1. I'm going to do these residues individually and then add them up. Our pole at z equals 1 is a simple pole, so we can evaluate it the way we did our previous examples. Multiplying the function and taking the limit, we're going to end up with 1 plus 2 over 1 plus 1 cubed, or 3/8. Our residue at z equals -1 involves a pole of order 3, because that is the power it is being raised to. So our n equals 3 and n minus 1 equals 2. So we take 1 over 3 minus 1 factorial times the limit of the second derivative of our function as z goes to -1. But before we take the derivative, we multiply our function by z plus 1 cubed. We're taking the second derivative of this chunk right here, which ends up becoming 6 over z minus 1 cubed. Take the limit, and then multiply by 1 over 2 factorial, and we get -3/8. So adding up our residues, we get 0, and our integral is 0. Alright, this one will be a little more complicated. Our function is e to the z over z cubed times z plus 5. We're going to limit our curve c to only include the pole at z equals 0. We take the residue of the function at z equals 0, which is a pole of order 3. 1 over 2 factorial times the limit as z goes to 0 of the second derivative of our function times z cubed. The pattern is the same. We use the quotient rule to find the second derivative of our leftover function, and it comes out to be z squared plus 8z plus 17 times e to the z, and that's over z plus 5 cubed, which when taken as z equals 0, you end up with 17 times 1 over 5 cubed. That's 125. Don't forget to multiply this by our 1 over 2 factorial. Our result is that the integral comes out to 2 pi I times 1/2 of 17 over 125, which is 17 over 125 times pi I. We don't necessarily have to have some kind of polynomial in the denominator in order to do our residue theorem. Let's try and evaluate the integral of this function, e to the 3 over z. This function has a pole at z equals 0. This pole, however, is a special kind of pole, called an essential pole. It's called that because we can't just get rid of it by taking limits and derivatives like we did before. But what we can do is expand the function into its infinite sum. If you remember, the expansion of e to the z is 1 plus 1 over 1 factorial z plus 1 over 2 factorial, z squared, plus 1 over 3 factorial, z cubed, and on and on and on and on. By plugging 3 over z into this expansion, we exchange all of the z's with 3 over z. And as you can see, this looks like a Laurent expansion with all powers of z going to negative infinity. Remember that the residue is the coefficient of the z to the negative 1 term. So our residue, right here, is 3. 2 pi I times 3 is 6 pi I, and that's the value of our integral. Alright, here's one for you. We're going to let C be the border of Western Europe. What do we get when we integrate a function around that border? Well, we're going to get 0. All the Poles live in Eastern Europe, don't you know?
Well, hey, that's it for me. Thank you all very much, folks.
Now, we're going to do our most grueling example yet. You may or may not ever come across one like this, but you can test us to see if we know how to do these residues. Our function is going to be the cosine of z over z minus 1 squared times z squared plus 9. We have 3 poles in this system, one at z equals 1, and one at z equals 3i, and one at z equals minus 3i. Our pole at z equals 1 is a pole of order 2. Now then, our integral is going to be the sum of these 3 residues. I'm going to do the residue at z equals 3i first. We take the limit as z goes to 3i of the cosine of z over z minus 1 squared times z plus 3i. Plugging in 3i, we find this to be equal to the hyperbolic cosine of 3 over 36 minus 48i. That's a complicated package, and I'm going to move it up to the corner to save it for later. For our residue at z equals minus 3i, we do the same thing, only since we are multiplying by z plus 3i, we are taking the limit of the cosine of z over z minus 1 squared times z minus 3i. This package comes out very similar to the one before. It's the hyperbolic cosine of 3 over 36 plus 48i. Now at last, we find our residue at z equals 1. Since the pole is order 2, we're going to be taking the derivative and also multiplying by 1 over 1 factorial, which is just 1. When I'm writing this out, I'm going to leave the term in our denominator as z squared plus 9, since it will be easier to work with. To take the derivative of this package here, we use the quotient rule to get negative 2z cosine z minus z squared plus 9 sine z over z squared plus 9 squared. I'm going to plug in z equals 1 directly into this package. We get negative 2 cosine of 1 minus 10 sine of 1 over 10 squared. We can divide through by 2 because that's a little easier to look at. Now I know this is really complicated to look at, but it's important to remember that these are all just constant numbers. We find a value for these and use them to find our integral. I've used a calculator to compute these values. When we add them up and multiply by 2 pi I, we get a grand total of 0.669i. Well, that's all I have on Cauchy's residue theorem. If you're interested, you should research some of the applications of this theorem. You can use the theorem to evaluate complicated real trig integrals or improper integrals that aren't even a part of the complex plane by making them into complex functions and integrating them and getting real results. It really is fascinating how we can use complex numbers, even though they are imaginary, to find real results. Well, thanks for watching this video, and I hope I can make more for you guys in the future.